welcome to this another video tutorial lecture. In this video lecture, we are going to discuss why is the Fourier transform so important. So we will start with the basic definition of the Fourier transform. What is Fourier transform? Basically, the Fourier transform is a mathematical function that decomposes a waveform, which is a function of time, into the frequencies that make it up. The result produced by the Fourier transform is a complex valued function of frequencies. So what basically a Fourier transform does, it converts a time domain signal into a frequency domain signal. So a time domain signal is a signal which is represented by time versus amplitude graph, and a Fourier transform converts this time domain signal into a frequency domain signal. A frequency domain signal is represented by a frequency versus amplitude graph. So this is a time domain signal, and this is a frequency domain signal. So basically, a Fourier transform converts a time domain signal into a frequency domain signal. So this is what Fourier transform does. Now, what is the advantage of converting a time domain signal into a frequency domain signal? So first of all, let's take one example how exactly Fourier transform converts a time domain signal into a frequency domain signal. So there is a mathematical expression for this. Suppose we have a signal x of t, a time domain signal, and we want to convert this signal into a frequency domain signal x omega. And Fourier transform converts this time domain signal into a frequency domain signal x omega. So mathematically, this x omega is defined as minus infinity to infinity integration x of t e raised to power minus j omega t dt. Now suppose you want to convert a signal x of t is equals to sine 2 pi f naught t. This is a time domain signal, and we want to convert this signal into a frequency domain signal. So we will use this formula. So x of omega or x of f are the same thing. Omega is angular frequency, which is related to simple frequency by this expression. Omega is equal to 2 pi f. Omega is your angular frequency, f is your normal frequency. So x of f is equals to minus infinity to infinity. Xt is your sine 2 pi f naught t, and this is e raised to power minus j. Omega is again your angular frequency. It can be represented as 2 pi f into t dt. Now we can use different properties like time shifting properties to calculate these, and Euler's formula to calculate the Fourier transform of this sine 2 pi f naught t. I am not going into the detail of that complete expression, how to convert, how to calculate this x of f. Rather, I am writing the expression for x of f here. So this comes out to be 1 by 2 impulse del f minus f naught minus del f plus f naught. So these are the two impulses, f minus f naught. One is at f naught and one is at minus f naught with the magnitude negative. So if we draw this magnitude spectrum of this x of f, we will get two frequencies. One is at f naught, which is having magnitude 1 by 2, and one is at minus f naught, having magnitude minus 1 by 2. So this is the you can say spectrum, frequency versus amplitude graph of this x of t, which is your sinusoidal signal. Now, what is the advantage of converting this sinusoidal signal into, if we plot the time domain graph of this xt, suppose this is your time domain graph xt. So this is sinusoidal signal. So it will start from 0, goes like this. Okay, so this is your xt. So this Fourier transform basically converts this time domain signal into this frequency domain signal. So what are the advantages of converting this time domain signal into a frequency domain? Now suppose we have different signals. So this is the first signal having amplitude, some amplitude, and this is the time axis. These are the time axis, and so this is the time axis, and this is the amplitude of first signal. This is the amplitude of second signal. This is the amplitude of the third signal, and this is the resultant of all signals A1, A2, and A3. So these are the time axis of these three signals. So this resultant graph, we cannot predict the frequency components present in these three signals A1, A2, and A3. Rather, we cannot predict the frequencies of these three signals by their individual time domain graph as well. So what we do, we convert these signals into frequency domain graph. So this is the frequency axis. So this is your frequency axis, and this is the amplitude of different components here. So the first one is A1. So this is represented, since the amplitude of A1 is low compared to A2, A3. So this is represented by this particular graph at some frequency, suppose F1, and the A2 is represented by this amplitude and at frequency F2, and this A3 is represented by this amplitude and at frequency, suppose F3. So in this frequency domain graph, we can predict the frequencies of these three signals, but in time domain graph we cannot say anything about the frequency, what frequency exactly, at what frequency they are oscillating. So why we are converting into frequency domain, a time domain signal into a frequency domain, and why we are calculating Fourier transform? Let's take one example of this. Suppose there is a 6 different signals here. So we have a signal y1 represented by this red line and having maximum amplitude and very low frequencies. And similarly, y2 is represented by blue line, y3 is represented by green line, y4 is represented by this cyan line, y5 is represented magenta, and y6 is represented by this gray line. So here we can clearly see that the amplitude of y1 is greater than y2, is greater than y3, greater than y4, and so on. And in terms of frequency wise, suppose the frequency of y1 is f1. So this f1 frequency is low compared to f2, low compared to f3, and this signal f6 is having maximum frequency here. Now suppose let us assume one hypothetical scenario in which these different signals represents different frequencies in a live orchestra. So suppose y1 represents the frequency of a musical instrument, like suppose this represents the frequency of a flute. y1 represents frequency of flute, y2 represents frequency of piano, y3 represent frequency of suppose saxophone, y4 represent frequency of some other musical instrument, and so on. And this y6, which is the highest frequency present in this signal, represent noise. And this is a high frequency, this is a high frequency signal, but having magnitude or amplitude lower compared to other signal frequencies. Now these different frequencies, what we able to hear in the live orchestra is the combination of all these frequencies. So this is the resultant. So y is the resultant of all these 6 different signals. So it is a combination of y1, y2, y3, y4, y5, and y6. So this is the signal which we hear in the live orchestra band. Now remember, this signal includes your noise signal as well, which is your signal y6. So this signal is mixed with all the other signals, and we are not able to figure out which from this graph which one is the noise signal and which are the signals coming from the musical instrument. So the Fourier transform helps to figure out which is the frequency component uh, which is creating trouble, and which is exactly is the noise signal, and we can filter out that signal. So if we convert these different frequency component into Fourier transform, so this is the resultant Fourier transform of these 6 different frequencies. Now here, these are the signals which is coming from the musical instrument, and this 6f is the frequency which is coming from noise signals, and we want to filter out this 6f frequency. So we can easily filter out by using a high pass filter. We can use a high pass filter to filter out this 6f frequencies, and these useful frequencies from f to 5f can be transferred easily. So this is the one particular application of Fourier transform. There are numerous other applications also of Fourier transform. Hope this video lecture will help you to understand what is the importance of Fourier transform, especially in communication. Thank you very much.